Okay, so we ended the last session with Grover's algorithm, which gives us a square root speed up over brute force search. Now I'm going to talk about a generalization of this idea called amplitude amplification. And just in case you didn't follow the previous talk and the details of the proof are too technical, the good news is you don't actually really need any of that for the rest of my talk. And in fact, this part of the talk is something that you don't really need to even understand the quantum details. I mostly want to explain how you can apply this framework and really give some examples in the second half, where we'll construct some algorithms using these ideas, but we won't need to know any of the quantum details that are going on under the hood. So that's kind of the power of this amplitude amplification framework, is that you can easily apply it and design a quantum algorithm without even understanding how that quantum algorithm is actually working. But you'll be able to analyze its complexity. So the rest of my talk will be, the ideas are based on quantum algorithms, but the intuition is actually kind of more of a classical algorithms intuition. Okay, so let's recall this guess and check algorithm that I mentioned at the beginning of the last session, where we sample, this is a bit of a generalization, we sample some x from our universe omega according to some distribution pi, maybe not uniform, it doesn't really matter, something that we know how to efficiently sample, and then we check if x is marked. So we check if f of x equals 1, and if so, we output x. And suppose that the probability when we sample according to pi of sampling the marked element is epsilon. So at every independent sample, we find a marked element or we succeed with probability epsilon. Then we need to repeat this thing 1 over epsilon times before we have constant probability of succeeding. So this is just the guess and check algorithm that I had before, but now I'm not restricting this to a uniform sample. We can sample from any distribution that we know how to sample from. So there's sort of an important special case of this kind of guess and check idea, which is the following. Suppose you have some algorithm A that outputs some correct answer with probability epsilon, and the complexity of this algorithm will denote by S. Okay, so often our goal is to construct an algorithm that is correct with probability at least, say, 9/10. But sometimes we first come up with a process that is correct with probability, like some smaller probability epsilon. And further suppose that you have a way of checking if the algorithm has output a correct answer. So when this algorithm when this algorithm fails, you know. In that case, we can imagine that the algorithm's output is like a sample, which is a correct answer, which we consider as being marked, with probability epsilon. Okay, so we sample some output of the algorithm, and it's correct with probability epsilon, and then we check if the algorithm is correct, and we keep repeating this some number of times, 1 over epsilon, or some constant times 1 over epsilon, and then with high probability, say 9/10, we get a correct outcome by the end of this procedure. So this is often called like success probability amplification, or so we say that we can amplify the success probability to constant, and then the complexity of doing this is 1 over epsilon times S plus C. So S is the complexity of the algorithm that succeeds only with probability epsilon, and C is the complexity of the procedure that checks if the algorithm actually output a correct answer. Okay. So this is certainly, if you've worked with algorithms before, this should be a very familiar looking thing. We often repeat an algorithm many times to amplify or boost its success probability. But this guess and check algorithm is exactly the form of the algorithm that we sort of used as the classical basis for Grover's algorithm. And actually, we can also make a quantum version of this more general guess and check algorithm where we sample non-uniformly. So let me just show that. More generally, the analysis that I showed you applies to the following situation, which is which is sort of a bit more general than Grover's algorithm, we prepare some state which has square root of epsilon amplitude on some good system. So this would correspond to, correct outcomes, or outcomes that we actually want. And then the rest of the amplitude is on some bad state that we are not interested in. And then we can repeat 1 over the square root of epsilon times the following 2 reflections. So the first is r sub pi, which is, again, it's just a reflection around pi. Okay, so this is just something that is going to fix pi and put a minus sign in front of anything orthogonal to pi. But now pi is this more general state. So when we talked about Grover's algorithm, pi was a uniform distribution, but now pi is some more general state. But as long as we have some way of preparing pi, we can still implement this reflection r sub pi. And then the second reflection, r sub m, it's also the same really as our checking reflection from Grover's algorithm. It's now going to put a minus sign in front of the good state, and it's going to fix everything orthogonal to the good state, or in particular it's going to fix the bad state. And by repeating these 2 reflections, we can get a state which has constant overlap with the good state. So again, if we suppose that we have some algorithm, this could be a classical algorithm, or it could be a quantum algorithm. And well, I guess the way I've written it, it's a quantum algorithm. It outputs some state pi. But if we have a classical algorithm that it instead is correct with probability epsilon, we could use that algorithm generally to prepare the state pi. And we'll also suppose that we have some algorithm that checks, that helps us implement the reflection r sub m. So this algorithm should check that, we're correct or that we're in the good state or something. Then we can amplify the amplitude on the good state to constant using complexity 1 over the square root of epsilon times s plus c. Okay, so this is called amplitude amplification because, whereas classically we try to amplify our success probability, this process amplifies the success amplitude. So it amplifies the amplitude on, some state that we're trying to prepare. And although this is amplifying the amplitude, what we often want to do is measure. So it is also kind of amplifying the success probability, but it's doing it in 1 over square root of epsilon, which is quadratically better than 1 over epsilon repetitions of the algorithm. So the high-level idea is that we know that classically, if you have an algorithm that succeeds with probability epsilon, and you have some way of checking if it succeeded or not, you can amplify the success probability using 1 over epsilon repetitions of the algorithm. But quantumly, you can do better. You can amplify the success probability using 1 over square root of epsilon repetitions of the algorithm. So this is kind of like a general way of sort of improving a classical algorithm by at most a square root. So now I'm going to talk about algorithms for collision finding, and we'll see some examples of how we can think of amplifying the amplitude of a classical algorithm. So in all of these algorithms, we can kind of start by designing a classical algorithm, and then we know we have a corresponding quantum algorithm that is maybe quadratically faster. Okay, so let's talk about collision finding, which again is the problem where we have some function, like a hash function h, and we want to find 2 inputs that map to the same thing. And we'll start off by assuming that there's many collisions, so we'll just say that the hash function is 2 to 1. So everything has a collision with something else. So one really naive algorithm that is not very good for collision finding is just to choose a uniform random x and y such that x of y, or that x is not equal to y, and output that. But of course, that's probably not going to be a collision. So this procedure where we just choose a uniform random x and y and output that, this succeeds with very low probability, okay? So again, supposing that h is a 2 to 1 function, so every element is in collision with exactly one other element, then the probability that a random x and y are a collision is like 1 over n. So we could see this really stupid algorithm for collision finding as having success probability like 1 over n. And of course, if we want a better algorithm, we need to amplify the success probability to a constant. So we can evaluate h on x and y and check if xy is actually a collision. And we can repeat this like 1 over epsilon times, so big O of n times, and then with constant probability, this will find us a collision. Okay, so then we're just going to talk about complexity just for simplicity in terms of the number of times we have to evaluate the function h. Okay, this is the query complexity. It's the number of sort of queries to h. And this gives us in this section the complexities, the time complexity of all the algorithms is like the query complexity with some log factors. So this is it's just a sort of simpler analysis. So we're only going to count the number of times we have to actually evaluate h. So that's why choosing a uniform random x and y has query complexity 0. And then checking if h of x is equal to h of y has query complexity 2, because we have to compute h of x and we have to compute h of y. And we repeat this n times, so the total query complexity is big O of n. So this is a very naive algorithm for collision finding, and it's not a very good algorithm. We can do much better than this. But before we do better than this, let's look at another stupid algorithm, because, why not? So in the second algorithm, we're going to fix some x in n. And now what we're going to do is we're going to sample our uniform random y, and then x and y are a collision with probability also 1 over n minus 1. And then we can check if x and y are collision, and if so, we can output x, y. We, of course, have to repeat this n times. So this is a slightly different algorithm. We're using the fact that because h is a 2-to-1 function, x is part of a collision. There's some y such that h of y equals h of x. So we were just going to fix some x and then look for the y that collides with x. So this is a slightly different algorithm, but it has the same query complexity, exactly. Okay, so now just to show how we can take these really simple classical algorithms and get quantum algorithms, we can consider the first algorithm, and instead of doing like this sort of classical amplifying the success probability by running it n times, we're going to use amplitude amplification to amplify the success probability. Okay, so now we get a quantum algorithm in the first algorithm. We get a quantum algorithm. So again, we have some like sampling step. And we're going to, instead of actually choosing a uniform random x and y, that's going to correspond to creating a uniform superposition. But I promise that you don't have to think about any quantum stuff when you design these algorithms. So you really don't. I mean, the complexity is going to be the same as choosing a uniform random x and y. And then we need to be able to also check if x, y is a collision, which we can do still in 2 queries. And now we just have a different formula for the complexity, because now there's a square root over the epsilon. Okay, so whereas in the previous slide, we have 1 over epsilon, and essentially you don't have to design a new algorithm, you just know that because of the existence of this classical algorithm, there exists a quantum algorithm that has complexity almost the same except with the square root, and that gives us a total complexity of big O square root n queries compared to classically the same algorithm, or the classical version of this algorithm takes big O of n queries. Okay, so this is just to show that you can kind of just design a classical algorithm, but you have also designed a quantum algorithm, and its complexity is better. Okay, and we can do the same thing in the second algorithm, so we can just instead, do amplitude amplification here. We still classically choose some x, and then we do amplitude amplification, and now we have, again, a square root. So this is, two quantum algorithms that require only square root of n queries to h. This is impressive because we sped up these classical algorithms, but it's not impressive because actually, classically, you can also accomplish the same thing. You can find a collision in a 2-to-1 function using square root of n queries. But that's just because we started off with a bad classical algorithm, and it also resulted in a suboptimal quantum algorithm. So any questions? This should be pretty simple. Okay, so now I would actually like to show you the optimal quantum algorithm. So to get a better quantum algorithm, we need to start with a better classical algorithm. Okay, so the classical algorithm will be following. So to start off, we're going to choose t values from 1 to n, and we're going to compute the hash function h on all of them. So we're going to compute some table consisting of x of I, h of x of I for all I from 1 to t. Okay. And then what we're going to do is we're going to search for some other x that is in collision with something in the table. Okay, so if you choose some uniform random x, then the probability that h of x will equal h of x of I for some x of I in our table T. So that's something like this. If we have this is our table, we want to find some new value x, like this is x equals 4, such that h of 4 equals 2, where 2 is something that's already in the table. Okay. And again, we are assuming that h is a 2-to-1 function, so everything has something that collides with it. And so the probability that a randomly sampled x is in collision with something in the table is going to be t over n, or approximately t over n. Okay? So, for all t things in the table, there's exactly one thing that collides with them, and if you sample any of those, we consider that a success, and you found a collision. Okay, so we need to repeat this big O n over t times to find a collision with high probability. So is this clear? So we first sample t random numbers and compute the hash on these numbers, and then we're going to search using sort of a classical guess and check algorithm. We're going to search for some x such that h of x equals h of x of I for one of our initial x of i's that we chose in the first step. Okay. So let's analyze the query complexity. So how many times do we have to compute h? So to sample uniform random x, that doesn't cost any queries to h. And to check if h of x collides with anything in the table, that just costs 1 query. We just have to query h of x. Okay? We don't have to query h of x I because that's already queried in the first step. Okay? And so the total query complexity of this searching for an x is going to be big O n over t. And of course, the query complexity of the first step is actually exactly t, because we are just computing for each of x of I on t different values x of I. Okay, so the total query complexity is like big O of t plus n over t. Okay, so this is just a classical algorithm. Okay, with query complexity t plus n over t. And this is optimized by setting t to be the square root of n, which gives us an algorithm with query complexity square root of n. So this is a classical randomized algorithm with complexity square root of n that finds a collision in a 2-to-1 function. Okay, so we had on the previous slide, we had these quantum algorithms that required square root of n queries, and now this sort of shows you that that's not impressive at all because we could also do that classically. And this is actually like kind of this algorithm doesn't actually make much sense classically because it actually turns out that if you just compute a table T of square root of n random elements with a hash applied to them, already with high probability there will be a collision in that table. This is related to the so-called birthday paradox, that if you get, the square root of 365 people together in a room with high probability, 2 of them will have the same birthday. So if we actually wanted to design a classical algorithm for finding a collision, a very simple thing that we could do would just be only the first step of this. So take square root of n random elements and compute the hash on them, and then sort them by their hash value to see if there's a collision. And with high probability, you'll find a collision that way. But we're not actually trying to design a classical algorithm, so it doesn't matter that this isn't a clever classical algorithm, because it turns out that the quantum version of this algorithm is an optimal quantum algorithm for this problem. So let's analyze the quantum version of this algorithm. So the quantum version of this algorithm, the first step is still classical. We're just going to choose x1 up to xt and store them in some big table. Okay, so that's just a classical sort of pre-processing step. And then we're going to use amplitude amplification to search for some x such that x collides with something in the table. So such that h of x equals h of x of I for some x sub I that we've already queried in the table. And so if we compare this to the classical algorithm, so when we analyze the classical algorithm, we have this, here we have this 1 over epsilon. But when we analyze the quantum algorithm, we get to put a 1 over square root epsilon here, which is better. So now we have square root of n over t for the second step. So the total complexity has a square root on the quantum part, on the search part. Okay, so this we've just designed a classical algorithm, and as I said, it's not really the most sensible classical algorithm. But when we look at the quantum version of this algorithm, which again, to analyze the quantum version of this algorithm, we don't need to know anything about how Grover's search works. I mean, you don't need the details that I showed you earlier to just be able to kind of blindly apply this. And we get an algorithm which, when we use t, when we set t equals n to the 1/3, this algorithm has query complexity n to the 1/3. And so the quantum query complexity of collision finding, it turns out this algorithm is optimal, so the quantum query complexity is n to the 1/3. You can also show a match in lower bound. Yeah?
Classically, there are better algorithms like Pollard row, where you try to find a period by hashing several times, then you lose this factor t in the beginning.
That's right. Okay, so the question is that classically there are better algorithms like you mentioned Pollard row. So there are some algorithms that some classical algorithms that cost only square root of n queries, but use only logarithmic space. So there's some clever
space.
Pardon?
Constant space.
Well, to store.
You only have to store 2 values.
Right, and the values have some size, right? So, logarithmic space, I guess. So there are classical algorithms that use only a log space and n square root of n queries, which is better than the classical algorithm that I just showed you, which costs square root of n queries but used also square root of n space. And then you can also consider parallel versions of these kind of row algorithms, like classically, that do better than square root of n, but then we should compare them to parallel quantum algorithms. So if we just consider like a standard like serial query model, we have this quantum algorithm that does n to the 1/3, and the best we could do classically is n to the 1/2. If we don't allow parallel algorithms. Yeah.
But the space complexity of this quantum algorithm also is something like n square root of n, right?
That's right. So the space complexity of this algorithm is n to the 1/3. So yeah, so it is worse. I mean, depending on what your goal is, the you know, this algorithm, it does use a lot of space, and although it is classical space, that is kind of an advantage. But you know, because the first step is classical. But I mean, like, it is a disadvantage that it uses like space that grows with n. But one advantage of this algorithm is that so it works in worst case n to the 1/3. So it succeeds with constant probability after n to the 1/3 steps, whereas these like row type algorithms that use a small amount of space, I believe all of them have some heuristic assumption where they succeed in expectation on the input. And I mean, I'm sure that these heuristics are very good, so in practice, this makes absolutely no difference whatsoever. But this, you know, for the purpose of theory, this is like a theoretical n to the 1/3 compared to, you know, if some of these classical algorithms are just heuristics. So you could also use the square root of n quantum algorithms that I showed a few slides ago, these kind of like naive algorithms where you just are sort of doing a quantum search for some pair that is a collision in just the most naive way. And this uses also only log space and gets you square root of n in like a rigorous and non-heuristic way. But I doubt anyone in practice cares that it's rigorous and non-heuristic at the expense of it being on a quantum computer. So
did you say that you only need classical storage space?
Yeah, so you store this table classically. The only thing is that you need to be able to access it in superposition. Like you need to be able to look something up in the table in superposition. So I mean, I guess maybe it's not fair to say it's completely classical space, but it's not. You don't need to have like some coherent superposition of tables of size n to the 1/3. Yep.
How crucial is the assumption of the hash function for these estimates that we can assume that for each x there's another x which is in collision?
So yeah, that assumption for the analysis to be really nice, we use that assumption, but what we really need is that if you, like, I mean, where we're using this is the fact that like we're saying that for any table, the probability that a random x collides with the table is t over n. So it doesn't, That's right. So, I mean, if the hash function has some property, some other property that makes it true that, you know, with high probability, if you choose a random t, there will be like at least, you know, something linear in t elements that collide with that table, then this algorithm would still work. So that the hash function needs some property that allows us to make this assertion. Otherwise, yeah, we can. I mean, you can also consider. We'll consider in like a few slides the case where there's only one collision. It's not really a hash function then, but this changes things dramatically. Yeah.
So you mentioned that the query complexity represents algorithm is optimal. If you see that it is optimal, that it's not algorithm, or
no, so it's not easy to see at all. It's so it's Yeah, there's a proof, but it's sorry. The question was whether it's easy to see if the query complexity is optimal, and it is not easy to see at all. And I mean, I don't even have a good intuition for why it's true, but okay.
So the optimal query complexity for quantum algorithm is n to the 1 over 3, and for classical algorithm it's n to the n square root.
Yeah.
Okay.
So the optimal quantum query complexity for for finding a collision in a 2-to-1 function is n to the 1/3, and the optimal randomized query complexity is n to the 1/2. So these are for finding collisions in a 2-to-1 function. So of course, if your function is k to 1, then you can do a slightly different analysis, both quantumly and classically, and you can do better. It's easier to find a collision if you have even more collisions. But we're actually going to consider a slightly different case, which is maybe a bit less relevant to cryptography, but is an important problem in quantum algorithms, and that is finding a unique collision. So we have a function which is almost 1-to-1, except that there's some unique pair, AB, such that h of A equals h of B. This problem is also sometimes called element distinctness, because it's equivalent to deciding if the function is 1-to-1 or has a collision. In the worst case, it would be if there's one collision. Okay, so the algorithm that I just showed you for collision finding, which I'll call, from now on I'll call BHT for the authors, Brizard, Hoyer, and Tapp. So we could consider applying the Brizard, Hoyer, Tapp algorithm to the problem of finding a collision when there's a unique collision. So what would happen in that case? I mean, suppose we use the Brizard-Hoyer-Tapp algorithm, but the function h has just one collision. So in that case, the algorithm would not necessarily succeed in finding the collision. So in Brizard-Hoyer-Tapp, we assume that h is 2-to-1, and then the algorithm will succeed, at least with high probability. But if there's a unique collision, the algorithm does not necessarily succeed. And in fact, it only succeeds if either A or B is in our initial set of T things that we query. Okay, so if A or B is in the table, then the Brizard-Hoyer-Tapp algorithm will succeed. But if A and B are both not in the table, then we can look for as long as we want, and we'll never find something that collides with the table, because such a thing does not exist. Okay, so the probability that Brizard-Hoyer-Tapp is successful is like T over N. So we are choosing, for Brizard-Hoyer-Tapp, I didn't specify how we should choose the initial table because it doesn't matter at all. But for this case, we'll now assume that we're choosing the table uniformly at random. So if we choose a uniform random table T to begin with, then the probability that it contains either A or B is like T over N. Okay, so we can consider Brizard-Hoyer-Tapp as an algorithm for this single collision version of collision finding that has a low success probability. So it has success probability only like T over N. But we know luckily what to do with such an algorithm. We can just amplify the success probability, and we can amplify the success probability using amplitude amplification. Okay, so we're going to, Brizard-Hoyer-Tapp already has amplitude amplification in it, but we're going to sort of apply outside of this another round of amplitude amplification. So we'll just sort of consider Brizard-Hoyer-Tapp as some algorithm. We don't care how it works. It's some quantum algorithm that returns us a collision with probability like T over N, and we can use amplitude amplification on that process. So to sample, we would run Brizard-Hoyer-Tapp and we would obtain some xy, which is a collision with probability like t over n. Okay, so it's a sample that is sort of good with probability t over n. And then to check, we'll just look at the output of Brizard-Hare tap, and we'll check if it's a collision. And I mean, actually, it's not completely clear what Brizard-Hare tap outputs if it doesn't find a collision. So the way I stated Grover's algorithm before, if Brizard-Hare tap doesn't find a collision, it would output fail. And so we could then easily check, if its output failed, and we know that it has not output a collision. But we could also suppose that if it doesn't find a collision, it outputs some random pair, and then we can check if that pair is a collision. But the point is, it's easier for us to check if what Brizard-Hare tap as output is in fact a collision. Okay, and now, so we know how to analyze such an algorithm that we've done amplitude amplification. So for the sampling procedure, we just run Brizard-Hare tap, and we know that this has query complexity t plus the square root of n over t in terms of the number of times we compute the function h. And then, of course, the checking step requires at most 2 queries. We just compute h of x and h of y. Okay, and then we plug this into our formula, which has a nice 1 over square root of epsilon, and we get complexity n to the 3/4 when t is equal to the square root of n. Okay, so the quantum query complexity of finding a unique collision, this problem, which is also called element distinctness, we just showed an upper bound of n to the 3/4. And in comparison, classically, the randomized query complexity is n. So for the classical case, of course, if you query the entire the entire domain, so you query h of 1 up to h of n, and then you can sort these values to find a collision, and this costs n queries. And it's also kind of easy to convince yourself that n queries are required classically, because imagine a deterministic algorithm where everything you query for the first n-1 queries is distinct, and then the last thing you query is one part of your collision. So you don't see a collision until the last thing you query. Okay, so this is an improvement over the best classical randomized algorithm for this problem. It is not optimal, so you can actually do better. There's an algorithm due to M- that solves this element distinctness problem using n to the 2/3 queries quantumly, and that is known to be optimal. But to improve over n to the 3/4 and get the optimal n to the 2/3, you require more machinery than just amplitude amplification. So to get this n to the 2/3, you have to use a technique that I'm not going to talk about, which is called quantum walk search algorithms. And I'll use that to segue into my next slide, which is further reading. So the optimal quantum query complexity for finding a unique collision, which this n to the 2/3 algorithm can be found online on the archive. This is due to M- from 2003. And this M-'s algorithm for this element distinctness problem, or finding a unique collision, it was actually so groundbreaking that it really inspired a new framework, which is even a generalization of amplitude amplification. So this framework, there's been several steps building on it, but it's most generally called like a quantum walk search framework. And there's different variations of it. A survey from 2008 talks about these quantum walk search algorithms, and in particular also presents Ambinus's algorithm. So the survey is probably a better place to start than looking at Ambinus's paper directly, because this sort of area of quantum walk search algorithms has matured and developed so much that it's, there are now much cleaner ways of presenting this element distinctness algorithm than in Ambinus's original groundbreaking paper from 2003. Okay, so for even more quantum algorithms, there's a comprehensive list, or at least its goal is to be a comprehensive list of all quantum algorithms, called the Quantum Algorithms Zoo, which you can find online. And this is a good resource for trying to check if, say you want to build a crypto system and you want to base it on a certain problem, but you don't know if quantum computers are already known to completely solve that problem. You can see what the state of the art is by checking this out. And then finally, there's a recent survey of quantum algorithms by Ashley Montanaro, and this gives a nice sort of high-level overview of the different types of quantum algorithms and sort of the state of the art in quantum algorithms at a kind of like approachable high level. All right, and that's all that I have. So if anyone has any questions about the handout, either from my talk or more generally from the handout, even if you don't want to ask them now, they'll also be around for the rest of the day. So please feel free to come and talk to me about any of this stuff. And thank you very much for your attention.